Remember the theorem we are trying to prove? So our theorem was that if G is a secure pseudorandom generator, PRG, then our scheme X that we defined previously was a secure encryption scheme under the single message eavesdropper game that we have defined. So when you think about our proof strategy, remember we do the proof using the contrapositive. So if there exists some PPT adversary A who breaks the scheme X, so remember, breaking scheme X would mean winning this game with 1/2 plus non-negligible probability. Then we are going to construct, remember this is a constructive proof, then we are going to construct another PPT adversary, B. Now what is that B going to break? B is going to break G. Now what does breaking G mean? It will distinguish between random and pseudorandom. So output of G versus some randomly picked value of the same length with non-negligible advantage. So the difference between the probabilities will be non-negligible. As usual, we are going to draw our boxes. Okay, remember the outside box will be B, and B is going to play the PRG game. What was the PRG game? Remember, B is given the security parameter and some value R, such that either R is picked randomly, okay, from n prime bit length values, or, okay, so this is one option, or a random seed was picked for our PRG, okay, and then this R was computed as G of that random seed. So this corresponds to the random case, this corresponds to the pseudorandom case. So R is either random or pseudorandom, which means eventually we need to guess that. We need to say random or let's say pseudorandom. Okay? Now inside there is this adversary A that we can make use of. Okay? A is going to play encryption game, the eavesdropper. So what's the interaction here? A needs to be given the security parameter, and then A will give us M0 and M1. Okay. Then we are going to return some value C that should be encryption of one of these to A, and finally A is going to output his guess some B prime. Remember, B needs to behave similar to the challenger of the encryption game here, and it needs to behave as an adversary in the PRG game here. So now our job is to fill in the code for B. For the security parameter, we will just pass on the same value. So this green security parameter will be the same as the blue one. There's nothing interesting here. For this encryption part, what B will do is B, it will pick a bit B, and then it is going to encrypt MB, but it does not, it needs to tie it to this random or pseudorandom value somehow. So it will compute C as R XORed with MB and then send that C. Now it receives back some B prime from the adversary. We have two options. If this B prime is indeed equal to B, so the adversary guessed correctly, then we will return as output, we will say pseudorandom, else B will return random. Intuitively, the reason here is that if R is a pseudo-randomly generated value, this way, then what we did here is exactly what A is expecting. We gave him an encrypted message, and then by our assumption that A breaks X, he should have 1/2 plus non-negligible probability here. On the other hand, if R was random, this is exactly one-time path, which we know is perfectly secure. Remember, there are three things we need to analyze. One, we need to show that B we constructed is probabilistic polynomial time. This is the code for B. Indeed, you can even argue this is taking constant time. Done. So we proved that B takes probabilistic polynomial time. The other thing we needed to argue is our simulation. Remember, here A is expecting a security parameter, we are giving him 1. Here A is expecting one of the messages XORed with some value, which is what we are giving him. So our simulation of the challengers is done. We are indistinguishable from a real challenger of the encryption game as far as A is concerned. The third part, remember, is the probability argument. We need to argue we need to argue that if A manages to guess this bit with non-negligible advantage, meaning A guesses this bit, so B prime is indeed equal to B with probability 1/2 plus non-negligible, let's say, some non-negligible function. If this is the case, we need to argue that our distinguishing probabilities, okay? So B outputting random, okay? So B outputting random, given that R was indeed random, so this probability and this probability, B again outputs random, but now it is given a pseudo-random value. We want to remember that this probability to be equal to this plus minus some negligible. In the usual case, breaking would mean some non-negligible here, okay? So if this is the case, this should be the case. This is what we want to show. Now, when you think about it, when would B output random? So take this probability, okay? B outputs random if this bit here, B prime, is not equal to B, okay? So this whole thing is the same as saying that B prime is not equal to B, given that R is a random value. So this is the same as this probability here. Now, when R is a random value, remember, what we are doing is exactly a one-time path. Therefore, by the perfect security of one-time path, B prime being equal to B has probability 1 over 2. B prime not being equal to B, again we'll have probability 1 over 2. So 1 minus 1 over 2 will give us 1 over 2. What about this one? This is analogous here. That probability will be the probability that B prime is not equal to B. Now given that R is a pseudorandom value. Now when R is pseudorandom, what we do here is exactly simulating the challenger for the adversary. When we give it the encryption construction X, we know that the adversary wins with 1 over 2 plus some non-negligible probability. Now, this is the probability that the adversary loses. If it wins with 1 over 2 plus non-negligible, it will lose with 1 minus this, and 1 minus this will be 1 over 2 minus non-negligible. So when R is pseudorandom, the adversary loses with 1 over 2 minus non-negligible probability, and whenever the adversary loses, B says R was random. Now we need to look at the difference between these probabilities, and the difference needs to be non-negligible. So here we have 1 over 2, and then here we have 1 over 2 minus non-negligible. And when we subtract these, what we realize is that this difference is non-negligible. There is a very similar way of arguing about this. So instead of directly saying non-negligible here, some sources says this is, let's say, 1 over 2 plus some epsilon. Now, if that's the case, 1 minus 1 over 2 plus epsilon will be 1 over 2 minus epsilon of n. And then the difference here, remember this is now epsilon of n, will be equal to epsilon of n. So if epsilon is non-negligible, if the adversary has non-negligible advantage in guessing this bit, then our adversary B will have non-negligible distinguishing probability. Going backwards, since we are assuming G is a secure pseudorandom generator, this value must be negligible. So epsilon must be negligible, which means the adversary's probability of guessing correctly would be 1 over 2 plus negligible. So if G is a secure pseudorandom generator, then X must be a secure encryption scheme.